Good morning. Black holes definitely have been in the frontier of research in the last many years, but definitely in the last decade with the discoveries of binary black holes mergers and the pictures of photographs of black holes and numerous prizes given to people involved in black hole research. And we really changed our understanding of black holes. When I was a student, this was the picture of a black hole. When you want to give a talk about black hole, you've shown that. We moved to here. When we want to show a black hole now, you show this. Now, this is much more complicated because in addition to just GR, which is the left part, it includes a lot of physics, a lot of plasma physics. And this means that understanding black holes is much more complicated. Not that GR is so simple, but now, in addition to the complication of GR, we have all the fantastic, rich field of plasma around black holes. And this is the current challenge. And you may ask, why are we doing that? So I can tell you that while preparing this talk on Monday, I had to take a break and go to my yearly checkup with my dermatologist. And after a quick look, 1 minute, he said, "You're okay." And then he glanced and said, "Well, the waiting room is empty, so I can ask you a few questions." And he said, "You must explain to me, I read somewhere that you can extract energy from black holes. How is this possible?" So then we spent the next 5 minutes with my attempt to explain this. So now I'll try to explain it to you. Okay, so this is the part of the collaboration that is actively working on that. Of course, everybody else is involved, but these are the people the PIs. This is just the PIs. If I wanted to have the postdocs and students, I wouldn't have room on a single slide. So I apologize to the postdocs and students who are really doing the work. These are the various PIs who have been contributing and their groups. And there was extensive collaborations here across this group. And almost more than half of the people here are collaborating with each other. There are some islands. I'm on one of these islands, but most of the people are it's a strongly interacting system. So understanding black hole. The first thing to understand that the new thing is understanding the gravitational wave signature. And this is one of the best observations of a black hole merger. And two things came out, well, many things came out in terms of populations and so on, but two things directly relevant to black hole physics emerged. The first part comes from the phase before the merger, from which one can estimate the masses and the parameters of these black holes. And from these estimates of the masses and the parameters, one can get a confirmation of Hawking area theorem, because you can estimate the mass of the remnant and estimate the mass of the progenitors and see that this is the area theorem is satisfied. The area is indeed growing in this merger with very high precision. So this is the first part, but this is not the only part. The second part comes from analyzing the signal after the merger. And here, with this recent measurement, for the first time, it was possible to identify not only the first mode, but also the second mode of the ringing black hole. And the second mode is very important because the second mode confirms that this is a Kerr black hole, not just a Schwarzschild black hole. The first mode will more or less give you just the mass. The second mode gives you the overtones, and from this you can identify Kerr. In anecdotal way, I can just look at it smiling because something like 40 years ago, we did the first calculations of numerical relativity from which we could calculate these modes, not in a case of emerging, but in a case of rotating collapse. And I'm smiling because this was done on a Cray 1. And considering what you're doing now with the simulation now, I just checked. My iWatch has more computational power by about a factor of 10 than the Cray 1 on which these calculations were done in the 80s. Well, so far I was talking just about pure GR, but now I want to go to the second part, and which is understanding black hole electrodynamics, which I call the missing part or injection. You can find everything about electrodynamics injection, but not this part. So this is what we have to do now. And you can ask yourself first why, because you can imagine, we all know that Dreiser-Nordstrom or Kerr-Newman are charged black holes, but these are just point charges, and they'll behave just like a big, massive charge. But macroscopic massive charges do not exist in nature. They're immediately neutralized by some other charged particle around them. So at first sight, you think about it, does that make sense? There is no black hole electrodynamics, or there is no interesting black hole electrodynamics in the real universe. But life is more complicated. And the story is that if you put a black hole inside a rotating black hole, inside the external magnetic field, and this, Roger told this to us about 50 years ago, that if you put a black hole inside the rotating black hole inside magnetic field, you get an EMF, you get an electromagnetic generator, which depends on the combination of the angular momentum, the magnetic flux around, and a very simple formula. Just get omega times phi, approximately. But it is not a purely conductive. It has the horizon resistivity, which is around 400 ohm. So you get a circuit like this, which is the black hole is the battery. This is the internal resistivity of the battery. And then there's an external load. Usually we think about this external load as the jet, but it could be other things, as we'll see later. And together you have an electric circuit. And if nature does it properly, as we all know, if the two resistivities are comparable, then the system is fairly efficient, and we can extract energy nicely from the black hole. So this was the answer to my dermatologist. I didn't explain it with so much details, but this is the basic idea. But if you think about it, it's actually slightly more complicated, because this black hole is actually a battery. Because the whole story depends on the rotation, and you have to charge the battery. And the charging of this battery is when you produce the black hole, or later on when you accrete on the black hole, when you make it rotate. So it's not an endless machine. It will depend on how much angular momentum you charged with in the beginning. So what do you need? You need magnetic field around the black hole. And here, the first place that the external plasma, external matter is playing a role, because the role of this external matter is to bring the magnetic fields to the vicinity of the black hole. Without this, we won't have this machine. So we need accretion flow to bring the charges, the magnetic field to the vicinity of the black hole. Once this is done, we can have this system operating. And we have a lot of data, a lot of observations to explain with the system. So the first, of course, is this beautiful picture of the black hole. And early work within this collaboration, even before the collaboration started, was done by members of the collaboration. Some worked one of the earliest theory paper explaining in details the GR of the orbits of the photons around the black hole, which are responsible for this signature. And other members, Bart, Richard, and Musko, contributed as part of the EHT team to the interpretation, to the modeling of this black hole, of this image. And this continues now when the three members that I mentioned are still members of the EHT team and contribute to expanding the interpretation. Now, M86. Why M86? Both M87 and SGRA are best described as RIAF, which is a radiation inefficient accretion flow. In these systems, the system is relatively dilute. It is not radiating efficiently. If it is not radiating efficiently, the disk puffs up, so you get a puffed up disk. And in these cases, we get here what is called MAD, a magnetically arrested disk. By the way, Ramesh told me that the first time he tried to publish a paper on MAD in AppJ, the editor objected because he said that disks cannot be MAD. But they insisted and the name stuck. So we have this magnetically arrested disk, and the magnetic field magnetic field here is so strong that the magnetic pressure resists the pressure of the matter, and we get a region in which we have just a magnetic field. And this is how this flow is usually interpreted. Or I will discuss later some other alternative explanation to what we see here, but we'll get to it. So because of this, most of the work which was done following, also by other groups, but also within this collaboration, was about radiation inefficient accretion and MAD system. This was motivated by this observation. This was the focus of this work. Now, one of the things which amazing is the flares that have been observed. This is a flare which have been observed by JWST. It's an infrared flare. Some of these flares are actually flaring was observed already in 2001 in X-ray. This is from, but this was an infrared flare which was observed recently. And this is the galactic center. And you see here at the time of the flare, the JWST observations. So we have flares coming from this accreting system. And the question is, how do we interpret them? Now, the amazing thing about these flares is the time scale, because the time scale, which is about 1,000 seconds, is not very far from the gravitational time scale of SGRA, which means that the source of the flare must be fairly close, 10 to 100 RG from the black hole, quite close. There are some ways to circumvent it, but apparently it is likely that this is really the location. And these have been modeled by various works. This is a work by Bart and collaborators, and I should have said it at the beginning of the talk. I want to thank Bart for really guiding me in all this zoo of simulations which have been done here. So everything wrong that I say is my responsibility, but everything right that I say is his responsibility. So, but this is one of these works led by Bart, in which we have, this is the MAD region. You see the matter is out, not near the black hole. This is the black hole. And these are reconnection zones. These are reconnection points in which particles are accelerated. We heard yesterday from Anatoly about particle acceleration in reconnection points. And the idea is that these are the sources of the flares which are seen here. And the location is consistent with this very short time scale. This is a simulation of how this works. And you see here instability growing here. And you see the structure here moving around. And you see the hotspots which are moving around here. And this is a simulation. And the basic idea here, I'll show another figure of this, is that relateral instability develops here very quickly. And this relateral instability helps initiate this reconnection. And this is what we see here. So, but I want you to look at the rotating pattern that exists here and remember it for a second. Now, a different group, the gravity team, has been watching SGRA for a long time, and with the ability to pinpoint the location of hotspots around SGRA. And this is the most famous one, probably also the first one of these cases, in which you see a hotspot moving around the center, around SGRA in this direction, moving around. If you assume, and this was the assumption done by the gravity team, that this is a Keplerian motion, that this is a blob of material which is hot and is moving in Keplerian motion around the black hole, then the rotation period would force you on assuming that, on getting that this is about 7 RG from the black hole, just very close to the ISCO. So this was advertised initially, not initially, this was advertised as observing motion of matter around the ISCO. However, if you look at it carefully, the distances, the observed distances, are not really consistent with this measurement of the distance. There is a tension between the observed size of the system and the periodicity, or the period of the rotation. And if you relax, so what we did here some 6 years ago, some purely phenomenological work, we relaxed this assumption that this is a Keplerian motion, and which tested various things, including Rayaf and super Keplerian pattern. And the idea was that this is not a blob moving around. This is a pattern which is moving around. and when you have a pattern motion, then the pattern doesn't have nothing to do, well, it should be the same order, but it is not directly the Keplerian motion. And then we get much better fit to the observation. I think this was our best fit here. Yes, you can see the high square. This is the best fit of some super Keplerian pattern moving at larger velocities. And I have shown this now, just after the previous simulation, because now we are going to check whether this particular simulation gives us something which is closer to this observation. Now, SGRA is probably mad, but there is no jet. And the jet is a natural feature of SGRA. So how this can be? And this is some very recent work done here by Galashnikova, Filipov, and Elliott Quatteret, and that shows that if you have a Bondi accretion from sufficiently large radius, then there is a jet here which tries to form, but the jet does not really get out. The jet is destroyed. Why it is destroyed, there are various interpretations. Maybe it gets kicked from the matter which is moving in a different direction, but the lack of a clear direction of the matter around the black hole prevent the formation of a jet here. So this may be an explanation. How can you be mad, but with no jet, which is very important if we try to explain SGRA with this model. Going to more flares and black holes, there is a question of how these things happen, and what you see here. Why did it stop? So you see here the buildup of a Rayleigh-Taylor instability that I mentioned before. This buildup of the Rayleigh-Taylor instability initiate the reconnection. And you see here this complicated structure that appears near the black hole. This is the black hole here at the center. This is some cavity which is formed due to this turbulent motion around the black hole. These are the magnetic fields. You see here, this magnetic field is in the equatorial plane, but here in the cavity, you get magnetic field outside of the equatorial plane. So you get the extremely complicated structure of this magnetic field. And the idea here was to try to calculate the emission here using synchrotron cooling. And these are attempts to fit the observed spectrum, time evolution of the system here in different phases. First, when this is building up, then steady state, and then the system is decaying. So this is further attempts to explain the detailed structure of these flares. In M87, we see flares which are much harder. And again, these are also interpreted with the same structure. So these are the observations. And you see here flares from Hess. This was a combined campaign of different observations. So we see Hess, Verita, Magic, and also radio and Chandra at the same time. And you see this flaring activity here. So how can we explain this? So what we have to do is, the idea is that we have to go to a very detailed plasma simulation. This is a simulation by Mehlav and Yanjay from St. Louis. And what we see here is a peak simulation, a peak GR MHD, a peak GR. If you need to include more plasma physics and more details into the system, we must stop doing just MHD. We must go to a peak simulation which can capture more details about the physics, and then we see this structure. So we see here, this is the flow, this is the magnetic field, and you see here something that will be the big theme here for the continuation. You see the stream pushing back into the matter. The black hole is influencing the matter and pushing back, and eventually there will be will form a gap here between the matter and the flow. And the important thing is that we see here transfer of angular momentum from the black hole through the system to the matter, and this pushes the matter back, and we see this empty region which formed here. And we also studied the details of the accretion physics here. So if you go to here, this is another simulation. This is the region very near the black hole, which was shown before. And here you have this reconnection, which is shown before. And the idea is that this reconnection is accelerating the particle, and this reconnection will accelerate some protons also, and they are the sources of the TeV. I see that I have to move a little bit faster, so I will go to the next topic, which is the magnetic area theorem. We began to see this story before. The fact that the magnetic field is moving out from the black hole. This is a fully relativistic GR simulation of collapse of a magnetar and formation of a magnetized black hole. But the black hole in vacuum. The black hole cannot remain magnetized because the black hole can have charge but not carry its own magnetic field. So the black hole has to get rid of the magnetic field, and this is the magnetic area theorem. We see here the black hole getting rid of the magnetic field and getting rid of it towards the situation of just a purely rotating black hole. So we see this motion of magnetic field expelled from the black hole, and we saw this also in earlier simulation, magnetic field pushing on the matter expelled away from the black hole. And here, the result here is that the final configuration is a quickly decaying magnetic field on a time scale of hundreds of gravitational time scales. And the asymptotic structure is something like always like a split monopole, almost independent of the initial configuration. And this is very quick. On this brief time scale, the system can behave like a pulsar, but for an extremely short time. But there is quite a lot of energy could be coming out in this pulse. If the magnetic field was large enough, all the energy of the magnetic field have to be ejected out. It can be 10 to the 48, 10 to the 49 ergs. So one can begin to speculate that this will produce, not speculate, this will definitely produce some monster shock, which is propagating outside. And you can speculate on the astrophysical implication. Maybe it's powering GRB, and what is also observed here is, if we go back to what was mentioned before, quasi-normal modes of the black hole can be seen in the resulting signature. Okay, I promised you that I should describe also an alternative picture of what is going on. So what we have seen in the simulations constantly is that the rotating black hole with the magnetic field is actually pushing matter out from the black hole. And this was pushed much forward by Roger and Nomi with the idea that what we see is not an accretion disk, but an ejection disk. And the idea is that, I won't go into all the details, that you have a very large, on a large scale there is an infall, and the matter is coming and bringing early on accumulating magnetic field in the vicinity of the black hole. But eventually, this black hole is interacting with the magnetic field which is around it, pushing things outside, as we have seen before, and producing here an ejection disk instead of accretion disk. And the idea is that this is what we see in M87 and SGRA. So the idea is that the black hole rotation drives the outflow and influence it. We definitely see such activity on a short time scale, but there are questions: can this last forever? Can the magnetic field remain bound for such a long time? Is this a steady state situation or just transient? I won't go into all that. Luckily, the organizer has organized a debate on this issue this afternoon. So I invite everyone to the rotation versus accretion debate, which will be this afternoon, and cover this exciting topic. Okay, let me skip and just go to the third part of my talk. I think that I'm starting to run out of time, and move to tidal disruption events. And first I'll ask why. And my point is that there's insufficient effort devoted to these events in the context of studying black holes, because a typical tidal disruption takes place at 25 RG. 25 RG is quite close. It results in a time-dependent accretion process, so it gives you a prospect on how accretion works in a time-dependent way. And it has a very nice time scale. The time scale of such event is few months to a year, perfect for a graduate student. I mean, for a GRB, it's too fast. I mean, it's 2 seconds, 100 seconds. It's not enough time to catch all the details. AGN, you know, they vary on millions of years. This is varying on time scale of few months, few years. So perfect topic for a human time scale. And we have to understand them. It's a fantastic tool. But it's difficult. It's difficult because of scales. We have the scale of the black hole. We have RT, which is larger, not much larger, but already a factor of 10 or 50. And we have A naught. A naught is the maximal distance, is the minimal distance to which the matter is getting, which is about 1,000 RG. So this is a challenge from a numerical point of view, a more difficult challenge than just steady-state accretion process. Now, one development which happened in this field, partly done here in this work, but also in other groups, so these two works are from here, that 4 different simulations with different initial conditions, different numerical methods, different assumptions about the physics, give the same result. And as far as I know, these are the only realistic simulations. There are other works which make various assumptions, and these assumptions are already put the answer into the into the picture before even doing a single calculation. But all these works are more or less realistic and go for a long time scales. And in all of them, you see one thing. The classical small disk, which was expected to form, it's not in this picture of Martin, but people expected that when the matter comes back, it will form a small disk of the size of RT, about 20 to 50 Rg. This disk is not seen in these observations, in these simulations. At the end of the simulations, we have a large cloud of a size of 1,000 Rg is a good order of magnitude, a large cloud without a clear small accretion disk. So to understand what is going on here, we have to understand this cloud. And this is a new simulation, but I don't have to go into it. This is a simulation that goes deeper than most simulations with a RP of 10 Rg, but it gives you the same result, even so it was going on deeper. You see the returning stream coming here. This is the vicinity of the black hole. This is the large scale. And again, no disk, large cloud forming here. This is simulation by Chan and Ryu from Colorado, Julian, which is here, and myself. It's not published yet, but we're just finishing the last touches. So what is the fate of this large eccentric cloud? It will accrete. This is a simulation of MRI. So I promised that I'll bring some magnetic fields even to TDEs. So this is a simulation of MRI. And you see here MRI in this elliptic flow. So we have elliptic flow to imitate this large cloud which is forming here. And we see that MRI is forming. We did it in 2 and 3D simulations. And the conclusion is that there is some interesting thing in this MRI, because if you look here at the effective alpha, which is, no, I don't have here the effective alpha, but if you look at the effective alpha, you see here that the effective stress tensor has 2 signs. Sometimes it's positive, sometimes it's negative, but it's still dominantly positive, and we get accretion. And this means that this large cloud will accrete on the time scales of few years. And actually, this is observed, and we think that this is the source of the X-rays, which have been observed, long-term X-ray that's observed in some TDE. More on magnetic field. This is the simulation that I've shown before by Ablomosov, Omer, and Amir, who are here, and Udi Nakar. And this is one of these 4 simulations that I've shown before. And these simulations are simulations of a magnetized star. So this magnetized star brings its own magnetic field. And the big question here is whether the magnetic field is amplified sufficiently to produce a jet. The answer, yes, is actually no and yes. The stretching of the magnetic field initially does not increase the magnetic field sufficiently to bring enough flux to the vicinity of the black hole to start a jet right away. This is what we want, because in some cases we see jets, and these jets need magnetic field, and the hope was that this will bring sufficient magnetic field. So initially, it does not do the job, but later on, you have this large sort of elliptical accreting cloud, and in this elliptical accreting cloud, the magnetic field begins to build up very quickly on a long time scale. So if I try to interpret this in terms of a realistic system, this will be a system in which a magnetic field will build up on a time scale of several years after at least several months after the initial merger, so it does not give rise directly to a jet, which we want to do. So far, I discussed typical TDEs, and these typical TDEs are happening at around 25 Rg from the black hole. But you have a new kind, a different kind of TDEs, and this is the case in which the star passes very close to the black hole. This is a star that passes this would have been the unperturbed trajectory of the star, so it would have made 2 turns around the black hole and then get back. But when it got to here, it was disrupted, and this is what's happening to it. All the bound material, unlike the usual story, all the bound material goes immediately to the black hole, and what we have here is just the unbound material. But the unbound material is moving with different velocities, and what we have here is something like internal shocks happening in this flow, because some parts, the inner parts of this outgoing material are catching out with the outgoing parts. They are colliding, and there are shocks, and these shocks leads to some of the material to fall back into the black hole. This is the center of the This is the center of the system. This is it looks static, but it is. But if you look at the scale, this is this almost spherical, circular cloud, which is expanding all the time, and some inflow is going on here at the center, and this system will be emitting at something like at the Eddington luminosity for sure. We don't know exactly to estimate which band it will be, but this have to be repeated with the proper with the detailed radiation transfer to get the luminosity and so on. This was done in Schwarzschild. Similar, let me show again the huge difference between this and a regular TDE. This is a regular TDE. The star is stretched, disrupted. This is the returning stream, and this is the late time evolution of the returning stream. So this is the 4 steps of a regular TDE. This is what's happening here. The star is stretched, but the very moment that the star is stretched, already half of it goes down the drain into the black hole. This is the outgoing part, which produced this beautiful spiral. Then the spiral becomes a ring because the inner edge of the spiral moves faster radially out than the outer edge. You get this ring, and then this ring expands. The shocks dissipate some energy, and some of the matter begins to fall inward. Time scale here will be much faster than here. Here the time scale is about a few months, about a month. Here the time scale for everything to rise will be about a week. Still good for a graduate student, even better. But we have to find them. And even so, this has to be very close to the black hole. It is still reasonable, because the chance to pass at short distance are proportional linearly and not like square of the radius. So significant fraction of the events should be of this kind, and particularly if you have an event around a massive black hole, then if the black hole is more than 10 to the 8 solar masses, most of the events should be of this kind. So it's something that we must be looking for, and as I said, this was in Schwarzschild, but we have now same simulations in Kerr, still only in the equatorial plane. In the equatorial plane, Kerr and Schwarzschild look almost the same. Now what we are trying to do is Kerr, but on a tilt with a tilted orbit, and this will be fun, but unfortunately I don't have the result to show here. I mentioned jets. There is a very nice work by Richard's group from San Antonio, in which they have a returning stream from a black hole, from a TDE, hitting a disk, And then this dense disk, which is in a mad situation, there is significant flux, significant magnetic flux, and they see a jet coming out from this situation. This is another attempt to do something similar. This is a tidal disruption in a TDE, a tidal disruption in an AGN, and what we are trying to do now, in this case, is to simulate a stream. This is the returning stream. It comes from here, but we inject it only here, intersecting a low luminosity accretion system with accretion of about 0.1 Eddington. And we see the disruption of the disk here. And the big question is whether this will give rise to sufficient amplification of magnetic field and jets that we expect to get here. But this is still work in progress. Also, since about 10% of black holes are in AGNs, it is just interesting by itself, even if this does not produce a disk, to understand what is the signature of these events, because these events are definitely happening somewhere in the universe. So I hope I convince you that to change a little bit your field of work and start doing these challenging simulations. But not too fast, because I have some students who have to finish their projects first. And now, going back to something completely different. S2 is out, S301 in. S2 got a Nobel Prize. S2 is the nearest star so far to SGRA, and its motion around SGRA demonstrated that there is a black hole there. Remo Ruffini doesn't believe it, but let's put it aside. So that there is a black hole, there, and we saw the big, we saw in the last periastron passage the big boost and so on. Now, S301 is much nearer. It is more or less the same apocenter, but it's much higher eccentricity. So the pericenter is only 280 Rg, with a velocity of about 25 kilometers per second at pericenter, and eccentricity of 0.9825, and 8.7 years orbit. So this was discovered by gravity. What I'm doing talking about it, why me? Well, when it was discovered, when Reinhard visited Jerusalem, he told me, well, this is an exciting thing. Do you think what will happen to the star? So I rushed to calculate, and I was extremely disappointed. I came back to the next group meeting, gravity group meeting, and said that it's a very boring object, because it's too far even for partial disruption. It's too far even for tidal heating to influence the orbit. So it's a boring star. Why should I care about it? Everybody in the room was very happy, because this means that this moves like a point source. And if this moves like a point source, using this object, we can measure the Kerr parameters of SGRA. So this is the likelihood, which is sort of described here, of how likely will it be to measure the Kerr parameter. This depends on the orientation of Kerr, because of the orientation of SGRA, because we have this orbit, and the orbit it will be influenced more or less depending on how the spin is related to it. So this is kind of direction of the spin. In some cases, we won't be able to measure. The up and down precession, but in some cases, which is in these directions, we will be able to measure it even with one orbit with the precision that gravity has today. So this is a possibly extremely promising way to understand the Kerr nature of SGRA. And
what's the time scale for the measurement?
8.7 years. This is the, oh yeah, it was detected recently, but then it was tracked back to, this is 21, maybe there is one more measurement from 2017. So this is the recent measurements. Once it was seen here, they went back to the archival data. If I'm not mistaken, there is one more point in 17, but don't take my word on that. I'm not sure. And the time scale to wait is 8.7 years, and it went around already once, so we had to wait 8.7 years for when it will come back. Excuse me?
Why wasn't it discovered before?
Excellent question. Unlike S2, it's a very small star. It's only 1.5. We don't exactly know, spectrum was not measured, but from estimate of the luminosity and so on, it's only 1.5 solar masses, which disappointed me, because if it was giant, it would have been disrupted. But it's not a giant.
Do we know the inclination?
No, we don't, well, we know the inclination, but we don't know the inclination relative to unknown.
The inclination relative to the sky?
Yeah.
We do.
Yeah. I don't know, I'm not sure. I'm not sure, sorry. One more. Yeah. Okay, one last thing about this. It's the origin. I said it's not exciting, but it's really very exciting. Why it is very exciting? Because with this eccentricity, it's almost certainly a part of Hill's disruption. That it was a part of a binary, and the other part was ejected as a hypervelocity star. And one of the things which we're trying to do now is to identify the companion. And if we manage to identify the companion, for sure, this will give quite a lot of information about the spin just by itself, identifying the companion. So it is an interesting thing. The eccentricity tells us almost with certainty that this was due to Hill's mechanism of binary. So with this, I will end. And these are my conclusions. And most important is this, that unlike Schwarzschild, which just sits and swallows stuff, this is the old black hole that we used to, Kerr is very energetic. It drags the space around it, pushes surrounding matter, produces jet, but also pushes the accretion disk, maybe preventing things to touch it. Nothing to do with the personality of these two people. Thank you.